All right, so in this video, we're going to be talking about distance in 3D. So distance in 3D, well, 3D math in general, like I've been saying, is just like math in 2 dimensions, except it has an extra component thrown out at the end of it. Distance in 3 dimensions is no exception to that rule. In fact, it's actually quite a good way of understanding that rule. It's a good way of seeing that firsthand. Um, and the reason why I say it's a good way of seeing that is because the way that we find distance in 3 dimensions is almost exactly the same as finding distance in 2 dimensions, except we quite literally throw a z at the end of that formula. And um, so I'm going to show you why or how in the course of this video. If you want the formula, if you want to see the formula first, and then if that helps you learn, then you can go to the end of the video, take a peek, come back to the front. But we're going to walk through and we're going to get there through this video. I'm going to explain the logic behind it. So say I've got these 2 points on this zx that drew here. We have this point on the bottom, which is point 1, x1, y1, z1, and then over here we have x2, y2, z2, respectively. Now, that's rubbish. Now, let's say we connect these 2 points and we want to find the distance between these 2 points, the split distance. So if this was a two-dimensional problem back in 2D, we would have used our distance formula that we had in 2D, which looked something like this: a squared plus b squared. Now, if it was a 2D problem, we would just take our x's and our y's and we'd throw them into this formula over here, and we'd be done, basically. It was just a whole plug and chug type of deal. It was a very simple affair. In 3 dimensions, we're actually still going to use this exact formula, and I'm going to show you how we're going to use it. It's a little bit more complicated. It takes some steps to get there because we have this z that's preventing us from plugging and chugging, but we're going to adapt this formula over here to suit our understanding of this problem, or to suit this problem rather. So what we're going to do is we're going to change this problem into something that looks a little more manageable with our understanding of math. So what we're going to be doing is we're going to be creating our triangle, right? So the distance formula that we had in 2D relies fundamentally on, well, it's essentially the Pythagoras theorem. So it relies on the fact that we have a right triangle. So we're just going to make one right now. Boom, we're done. Almost, not quite. So this is our right triangle, and we made it by adding a new point. And this point is going to be directly below, still need eraser. This new point is going to be directly below point 2. So because it's directly below point 2, we know a few things. We know that this point is going to be x2, y2. We don't know the z value from that. What we do know is because this point is directly in line with point number 1, we know the z value is going to be z1. And we're making it so because we want these to have a perfect right angle. That's why we made it in such a position. All right. So how exactly is this original 2D formula going to help us out? Well, what we're going to be doing is we're actually going to be using the exact same original distance formula. We're going to say that this side, this long side is going to be A, and this height side is going to be B. Now, what you notice by creating this point and making this triangle, we are actually able to find the distance of A now. We're able to find this distance. We're also able to find the distance of B. So we actually can right now, use this formula. Square root of a squared plus b squared. We just have to find a. So what we're doing really is we're breaking down this problem. The way we find a is we use our exact same original 2D formula. So we're going to throw that back right there. And what we're going to be doing is we know that z is the exact same value. We know it's on the same level. So we can kind of just ignore z now, and we can use our original formula. we can say that a is equal to the square root of x2 minus x1 squared plus y2 minus y1 squared. And boom, that's it. It's quite literally that simple. Now, how do we find the length of b? B is literally just the difference in height of z, because we said it's right below it. So b is just going to be z2 minus z1. Now that we have our a and b value, we square them and we plug it back into the original equation. So now we get square root of the square root of the square root of x squared, x2 minus x1 squared plus y2 minus y1 squared. Now remember, all this is square rooted because this was our a value, because we're just throwing this into there. But because a in our original expression is squared, we're squaring this again. And then our b squared is going to be just this b value squared. So it's just going to be z2 minus z1 squared. We can simplify this part right here by removing the radicand, because we are squaring it. Simplify this into now being d is equal to the square root of, now remember, because we're squaring this, we can get rid of this radicand. So we can just write everything underneath it now, which is going to be x2 minus the quantity x2 minus x1 squared plus the quantity y2 minus y1 squared. And then our z doesn't change, that just drops down. z2 minus z1 squared. And boom. So check it out. This is our final 3D distance formula. It looks pretty similar to this, except we have an extra z squared thrown in at the end. All right. Thanks for watching. As always, if you have any feedback, if you have any questions, please leave it in the comments below. Thank you very much.